In this lecture, we'll take a look at linear systems of equations. First, before we start, let's take a look and review the case of two equations with two unknowns. Here is a simple example of a system with two equations and two unknowns, x and y. We can solve this system quite easily using, for example, the elimination method. If I subtract x on both sides of equation 1, it says 2y is equal to 4 minus x. Then the second equation reads 2x plus 2y, and 2y was 4 minus x, and that should be equal to 2. And this simplifies to x equal to minus 2. Replacing x with minus 2 in this equation, we have 2y is equal to 6, or y is equal to 3. We can check that this is a correct solution in the first one. Minus 2 plus 2 times 3, that's precisely 4. And the second equation, 2 times minus 2 plus 2 times 3. If you have more equations and more variables, then this method is quite cumbersome, and we'll look at a more efficient method, solving systems of equations. There is also a nice geometric interpretation of this solution. If you look at the first equation, it says x plus 2y equal to 4. We can make a plot of all the points in a Cartesian coordinate system that satisfy this relation. A simple way to make such a plot is to use Wolfram Alpha. If you go to Wolfram Alpha at wolframalpha.com, then you can just type plot x plus 2y equal to 4 and hit enter. And you will see all the points that satisfy the first equation. For example, this point here where x is 0 and y is 2 satisfy it, because then you have 0 plus 2 times 2, and that is 4. Similarly, x equal to 4 and y equal to 0 is another point. And since this is a linear equation, all the points must be on a straight line like this. Here is the second equation, 2x plus 2y equal to 2. And if you type plot x plus 2y equal to 4, comma 2x plus 2y equal to 2, Wolfram Alpha will plot both of these straight lines in the same diagram. So here they are. The blue one representing equation 1, and the purple one representing equation 2. And there is only one point that satisfies both equations, and that's when x is minus 2 and y is equal to 3. It's possible that both of these lines have the same slope. For example, it might look like this, where the blue represents the first equation and the red line the second equation. If they have the same slope, there will be no point which is on both lines, and in this case the system of equations has no solution. Here is a simple example. This system can have no solutions because it's impossible for x minus y to simultaneously be equal to minus 1 and plus 1. Another possibility is that both of the lines have the same slope and the same intercept. And in this case there are an infinite number of solutions. Every point on this common straight line will be a solution. And here's a simple example. These two equations are actually the same equation, which we can see if we multiply the first equation by 2. So we've seen examples of no solution, one solution, and an infinite number of solutions. What cannot happen is that you have precisely n solutions where n is greater than 1. For example, it's impossible to have precisely 2 solutions, and that's because each equation represents a straight line. To have 2 solutions, I would need the second line maybe to look something like this. then I would have two solutions. But then the red curve cannot represent a linear equation because it's not a straight line. And so returning to the more general case, I want to generalize this, allowing not only two equations, but n equations. And I want to generalize it, allowing not only two variables, but m variables. So we will consider the case where the number of equations is not the same as the number of variables. If I have m variables, it's more convenient to use the notation x1, x2, and so on all the way to xm for the variables instead of x, y, and z. So the setup is then this: a linear system of n equations in m unknowns, m variables, or just an n by m system, then looks like this. There are n rows in this system, one row for each equation. If you look at the first equation, the first row on the left hand side, you see that we have x1, x2 all the way to xm. Those are the m variables. In front of each variable is a constant denoted by a, and we need two subscripts for the a. The first subscript denotes on which row we are, and the second subscript denotes which x variable it belongs to. And on the right hand side is another constant denoted by b. If we compare the example we started with this general notation, we see that in our example m is equal to 2, two variables, and n is equal to 2, two equations. The x variable in our example corresponds to x1 in the general notation, and the y variable in our example corresponds to x2. We see that a1, 1, that's the constant in front of x in the first equation is 1, a1, 2 is 2, the constant in front of y in the first equation, a21 is 2, and a22 is 2. And finally, b1, the right hand side constant of the first equation is 4, while b2 is 2. What you will never see in a system of linear equation is, for example, x3 squared, or you will never see a product of the x variables, such as x1 times x2. That would make the system non-linear. We have some terminology. We say that the system is balanced if we have the same number of equations as we have unknown variables. We call the system overdetermined if there are more equations than variables, and we call it underdetermined if the equations are fewer than the number of variables. A particularly interesting case of a linear system of equations is a system where all the constants on the right hand side are 0. That is, all the b's are 0. Such a system is called a homogeneous system of equations. So a homogeneous system of equations looks like this. If any one of the b's on the right hand side is non-zero, then it's called a inhomogeneous system of equations. Moving on to some examples. Here is a balanced system, a 2 by 2 system. Here is an example of a overdetermined system, more equations than unknowns. And here is an example of an underdetermined system, which is also homogeneous, the first two being inhomogeneous. And we will discuss general techniques for how to solve such a system. Before we continue, let us first discuss what we mean by a solution to a system of equations. So by a solution to a system of n equations in m unknowns, in particularly to a linear system, we mean an m tuple of numbers that satisfy all the n equations of the system. A tuple is simply an ordered list of elements. And an M tuple is just an ordered list of precisely M elements. In this case, we need the elements to be numbers, and these numbers must satisfy all the equations of the system. For example, in this simple example, we would write the solution as -2, 3. Just like for the 2 by 2 system, an n by m system may have no solutions at all, in which case we call the system inconsistent. It may have exactly one solution, or it may have an infinite number of solutions. Those are the only three possibilities. It cannot have n solutions where n is greater than 1. We'll prove this formally in an exercise, but a geometric perspective is more useful. For example, in a 3 by 3 system, each equation will represent a plane in 3 dimensions. And if you think about 3 arbitrary planes in 3 dimensions, you'll realize it's absolutely impossible for 3 planes to intersect at exactly 2 points. If they intersect at 2 points, they must intersect at every point in between these 2 points. If the system has one or an infinite number of solutions, then we call the system consistent. Homogeneous systems are special because they are always consistent. A homogeneous system must have one or an infinite number of solutions. That's not hard to understand if you look at the homogeneous system. All x's being equal to 0 must always be a solution to a homogeneous system, since the left-hand side of each equation will evaluate to 0. Finally, we use the terminology a solution set of a system, and that is the set of all solutions. So the solution set might be empty, it might have one element, or it might have an infinite number of elements.